Hello class. Today we're in Chapter 2, Lesson 4, Direct Variation. We're on page 84 of our textbook and we have an illustration here, a cartoon, with a gentleman looking at a stone and he sees a shadow which is separate from the stone. He picks up the stone, carries it over, drops it right next to the shadow and says, "I can't stand this order." Well, let's read on. At any given time during the day, the length of an object's shadow depends on its height. Here is a table showing the heights at some different objects and the length of their shadows at a certain time in the afternoon. So we see a table, we have height. Let's go ahead and draw off our table up here. So we have H. I'm just going to put an H here for height and an L for W. And we see 1 to the height being varying from 1 to 6. Okay, so we have 1, 2, 3, 4, 5, and 6. And we see that the length of the shadow is 1.5, it's 3, 4.5, 6, 7.5, and 9. Okay, now there's a pattern here. It says because to each height there corresponds exactly one shadow length, this is the table of a function. We learned that in the previous, okay? There's only one corresponding y value to an x value. So, it is easy to see that the two variables in this function, height and shadow length, vary in the same way. If the height is doubled, for example, then the length is also doubled. Let's just take a look. So we double the height. Let's see. We went from 1 to 2, right? It's doubling. And we see that over here it's doubling as well. Okay? Let's say we go from 2 to 4. Let's double that. All right? From 2 to 4 and from 3 to 6. So it's doubling. So we see something in peculiar. We see a pattern here. And that's going to be a term that we're going to learn. If the height is double, for example, the shadow length is doubled. If the height is tripled, then the shadow length is tripled, and so on. Because of this, the two variables are said to vary directly. And the function relating them is called a direct variation. Okay? And we're going to learn about what's called an inverse variation, which is another term. But we're going to learn first the direct variation. It says the numbers in the table for this shadow function have a simple pattern. And so the function can also be represented by a formula. If we sat down and did what we did in the previous lessons, we could figure out a formula. What would that formula be? Well, they're giving it to us, so let's just go ahead and write it down. It says here, in each case, the length of the shadow is 1.5 times the height of the object. So letting x represent the height and y represent the shadow, we can write y is equal to 1.5x. So every time we take an x value, we multiply by 1.5, we're going to get our y value. Okay, so here's our formula. Now let's take a look at the top of page 185 and we read on. If the 6 points of our table are located on a graph as shown on the left below, they seem to lie across a straight line. So we have our 6 points. Now notice we do have some decimals here, so we need to be very careful. In fact, I would probably just go ahead and first get my black marker and let's go ahead and write. Now I know that they only put the 5 here. We have 1, 2, 3, 4, 5. Okay. Now we can go ahead and do that. 1, 2, 3, 4, 5. Now, when I have decimals, I like to be very careful. It's very important because we can easily lose our place on a graph. So in this case, I'd like to go ahead and put my numbers all the way across. It's just maybe a few seconds more work. Okay. In this case, I'm just going to go out to 9. Obviously, we don't want to do this from 1 to 100. If we have to, we have to. But we probably wouldn't if we were drawing a graph that big, unless we're plotting maybe 100 numbers or 100 points. So here we go. We have all of our our numbers going across their x and y axis. Now we can go ahead and plot our points, and if we plotted our points, we know we go to the first point 1 and 1.5, so we go 1. Now here, with the help of the 1 and the 2 in between, being able to see that, we know that this is 1.5. So let's put that in there. And then we have 2, which would be 3, so that's pretty simple. That lying right on in between those two lines, or right on the intersection. If we go to 3, and we know it's 4.5. So again, I have to go right in between the 2, in between the 4 and the 5, and that's 4.5, because we know that's exactly in the middle. And we go out to 4, it would be 6. Now you could see that it looks like they just lie across a line. We're forming a straight line here. 5, we go all the way to 7.5. Okay, and then we go out to 6, we go all the way to 9. Okay, so here we have our coordinates all plotted. Now we're going to draw a line. Now in drawing this line, what we're saying is that not only are these answers to this particular formula, but that everything that is on the line would actually be an answer. So I'm just going to go ahead and make a thin line so you can see our points here, and I'm going to extend all the way out from the origin. And I'm doing that for a reason, because the 0, 0 value is also part of this in terms of our table, and we'll discuss that just a little more at length. It says here, it is possible to prove that every point whose coordinates fit the line y is equal to 1.5 lies on this line. So all of our answers, we could plug in many values, not just 1, 2, 3, 4, 5, 6. We could do 1.5. We can do 2.5 as a height. So what would it yield as a y value? Well, this graph is showing us all the answers without having to plot every single one, because there are really an infinite number of numbers between, say, 1 and 2. So let me get my marker back here, and let's continue. Moreover, every point on the line has coordinates that fit the formula. Because of this, we can draw the line through the points and refer to it as the graph of the function. So the line itself we refer to as the graph of the function. The formula and line give a much more complete picture of the function than do the original table of 6 points. If we just look at those 6 points, we might say, well, those are the only answers. Well, if the criteria for the answer were that it needed to be a whole number or an integer, if you're familiar with an integer, whole number, those are whole numbers like 1, 2, 3, 4, 5. If those were the only possible answers, then we couldn't draw this graph because we would be limited to just those points. But if we're not limited, you might say, well, what are the other answers? Well, everything again on that line, anything, any point that you can find on this line with an x and y value would be an answer to this. So if you were to look over here, just over here at 2, you might say, well, that you're saying this is an answer, and I say, yeah, that's an answer. Well, what's its corresponding y value? Well, if you did the math, you would know that 1.3333 would actually be the answer. 1.33333 times 1.5, and I say 333, it's actually an infinitely 3333, it's 1 1/3, would yield the value of 2 for a y value. So again, that's one value. Now we don't have that on our table, but every point that lies in this graph infinitely outward, as far as it extends, would be an answer to this formula. Okay, so for example, we see that if x is equal to 0, then y is equal to 1.5 times 0, which is equal to 0, which is why we have the coordinate point here, 0, 0. We're at the origin. This means that the point 0, 0 is part of the graph. The line intersects the axis at the origin. So now we have a definition here. We've got a little green arrow. It says, in general, a direct variation is a function that has an equation of the form y is equal to ax. So we have what's called a form now. Now, a form and a formula, they're two different words. A form is sort of a picture of a formula. We have a formula here, right? We see this formula. Now this is a form of it, and it's just basically telling you that it has 2 arms, 2 legs, and a head, okay, and a body. Well, not quite, but let's just say that the form of a human body, we know that there's an arm, there's 2 arms rather, there's 2 legs, there's a head. That's a form. Now, does that mean we all look identical? No, we all look different, but we all generally have, you know, for generally speaking, 2 arms, 2 legs, and a head, let's just say. So over here, we have a y value, we have an x value, right? And then we have an a value, and you say, well, what's the a value? Well, in this case, the a value is 1.5, okay? Now, the a value has a definition, and we say that And actually part of the definition is in which a is a fixed number other than 0. Okay? Because if it's 0, then none of this makes any sense because you wouldn't have a graph. Because anytime you multiplied anything by 0, so in other words, if we had y is equal to 0 times x, what they're saying, it can't be this. Why? Because no matter what you put in for an x value, it will be 0. So the answer to this will always be 0, 0, which means you wouldn't even have a line. You would just have 1 point. Okay? But let's go back to our a value here. It says here the number a is called the constant of variation. In the example of a shadow function, the constant of variation is 1.5. The graph of every direct variation is a straight line that intersects the origin. Okay, so we have two things here that we saw. This last paragraph tells us quite a bit. It says that the number a, you might say, well, that's not a number. Well, a is just a representation. Let's call that the head, okay? There's a head here. Does every head look the same? No. Especially we all have different haircuts, obviously. But let's just take a look, and we're saying that this is the letter A. In this formula, a is being represented by 1.5, okay? So the number a is called the constant of variation. We say the number because there will be a number value there. It's not necessarily a variable. The variables are x and y. A is just being represented in a form, okay? Remember, if I show you a picture of a deer, okay, and you were to go hunting for deer, so you're looking for a deer, and maybe you have that picture with you while you're hunting, and it's a form of a deer. And when you see a duck, you're going to say, "That's not a deer. I can't. That's not. I'm trying to catch a deer. I'm hunting for deer." So you're looking for a deer. When you spot the deer, you say, "Oh, I think that's a deer." Well, it doesn't look exactly like the deer, but it has pretty much the same, the body, the shape. Maybe it has some antlers. Then you're saying, okay, this is a deer. So it's a form, and this is a form of. So if I were to write another formula, let's say y is equal to 5x. Now that's completely different, okay? These are two different deer, aren't they? But they're in the same form, okay? There's a y, which is over here on the left of the equal sign, and then we have a, which is the 5, and then we have an x variable, which is over here. So when we're looking at things, we have to look at them in terms of form. And that's going to be very important throughout this class that you understand forms, being able to see the form of a particular equation or a particular type of expression. You have to be able to identify these things and say, oh, okay, I see the y, I see the x, and I see the a, though it doesn't say a. That's the number, quote unquote, a. There it is. So there's the form. So once you identify it, you say, oh, that's a direct variation. And I know Mr. Cartagena taught me that a direct variation is a line that intersects the axis at the origin, and it's a straight line. So the form's going to help us to identify and relate it to the graph and maybe to other things as we go further on. That's the end of chapter or lesson number 4.